Every single day, millions of cars, trucks, airplanes, ships, and factories rely on fuels that all begin as the same raw material: crude oil. From the gasoline that powers family vehicles to the jet fuel that keeps aircraft flying across continents, nearly every modern transportation system depends on products refined from petroleum. Yet very few people ever stop to wonder what actually happens after crude oil is pumped from deep beneath the Earth's surface. How does a thick, black liquid become dozens of clean, highly specialized fuels and industrial products? The answer lies inside one of the most advanced industrial facilities ever built: the oil refinery. These enormous complexes combine chemistry, mechanical engineering, automation, and precision control to transform crude oil into the products that keep modern civilization running every hour of every day. Crude oil is not a single substance. Instead, it is a complex mixture containing hundreds of different hydrocarbons, along with sulfur, nitrogen, oxygen compounds, salts, water, and tiny amounts of metals. It formed over millions of years as ancient marine plants and microscopic organisms were buried beneath layers of sediment. Heat and pressure slowly converted this organic material into petroleum, which eventually became trapped inside underground rock formations. Oil companies locate these underground reservoirs using advanced geological surveys and drilling technology, before extracting the crude oil through production wells. Once it reaches the surface, the crude oil begins a long journey by pipeline, tanker ship, rail, or truck, until it finally arrives at an oil refinery. Before refining can begin, every shipment of crude oil is carefully analyzed in specialized laboratories. Engineers need to know exactly what type of crude oil has arrived because different oil fields produce different qualities of petroleum. Some crude oils are light and contain relatively few impurities, making them easier to refine. Others are heavier and contain higher concentrations of sulfur, metals, and complex hydrocarbons that require additional processing. This initial testing allows refinery operators to adjust temperatures, pressures, and processing methods to maximize efficiency and product quality. After inspection, the crude oil is pumped into enormous storage tanks that can each hold millions of liters. These tanks are equipped with sophisticated monitoring systems that continuously measure temperature, pressure, liquid levels, and product quality. Before entering the refining units, the crude oil passes through desalting equipment where water is mixed with the oil to dissolve salts and remove dirt, sand, and other contaminants. Electrical fields then separate the water from the oil, preventing corrosion and protecting valuable refinery equipment from damage during later processing stages. Once cleaned, the crude oil enters a network of heat exchangers. Instead of wasting heat produced elsewhere in the refinery, engineers recover it and use it to warm the incoming crude oil. This significantly reduces fuel consumption and improves overall energy efficiency. The partially heated oil then enters massive industrial furnaces where temperatures rise to nearly 400 degrees Celsius. At these temperatures, most of the crude oil becomes a mixture of hot liquid and vapor. This heated mixture is now ready for the most important process inside the refinery. The mixture flows into the atmospheric distillation tower, one of the tallest structures in the refinery. Although the equipment looks extremely complicated from the outside, it operates using a simple scientific principle. Every hydrocarbon has its own boiling point. As the hot vapor rises through the tower, the temperature gradually decreases from bottom to top. Heavy hydrocarbons condense first because they require higher temperatures, while lighter hydrocarbons continue rising until they reach cooler sections where they also condense. This allows engineers to separate crude oil into multiple useful fractions without changing their chemical composition. Near the very top of the tower, the lightest petroleum gases such as methane, propane, and butane are collected. These gases are widely used for cooking, heating, and as raw materials in the petrochemical industry. Slightly lower in the tower, naphtha is separated. Although naphtha cannot yet be used directly as gasoline, it becomes one of the most valuable refinery products because it serves as the primary feedstock for gasoline production and many chemical manufacturing processes. Further down the tower, kerosene is collected. After additional purification, this fraction becomes aviation fuel used by commercial and military aircraft around the world. Below the kerosene layer, diesel fuel and heating oil are separated. These products power trucks, buses, trains, ships, heavy construction equipment, agricultural machinery, and backup power generators. At the bottom of the tower remain extremely heavy oils and thick residues that are later processed into lubricating oils, paraffin wax, petroleum coke, asphalt, and many industrial products. Although distillation successfully separates crude oil into different groups, it cannot produce enough gasoline or diesel to satisfy modern demand. This is why refineries rely on additional conversion processes. One of the most important is fluid catalytic cracking, commonly known as FCC. In this unit, extremely large hydrocarbon molecules are broken into much smaller molecules using high temperatures and finely powdered catalysts. This process dramatically increases gasoline production while making every barrel of crude oil far more valuable. Another essential process is hydrocracking. Unlike catalytic cracking, hydrocracking combines high pressure, elevated temperatures, hydrogen gas, and specialized catalysts to both break large molecules and remove impurities at the same time. The result is cleaner diesel fuel, premium jet fuel, and other high-quality petroleum products that meet modern environmental standards. Without hydrocracking, many heavy crude oils would produce significantly lower amounts of useful transportation fuels. The refinery also performs catalytic reforming, a process designed to improve gasoline quality rather than simply increasing its quantity. During reforming, hydrocarbon molecules are rearranged into structures that have much higher octane ratings. Higher octane gasoline allows modern engines to operate more efficiently while reducing engine knocking. An additional benefit of catalytic reforming is the production of hydrogen, which is reused throughout the refinery for hydrotreating and hydrocracking operations. Hydrotreating has become one of the most important refinery processes because environmental regulations around the world require cleaner fuels than ever before. In hydrotreating units, petroleum products react with hydrogen over advanced catalysts that remove sulfur, nitrogen, oxygen, and trace metals. Removing sulfur is especially important because sulfur dioxide released during combustion contributes to air pollution and acid rain. Today's ultra-low sulfur fuels are only possible because of these sophisticated purification systems. Modern oil refineries are controlled almost entirely by automation. Thousands of sensors installed throughout the facility continuously monitor temperature, pressure, flow rates, vibration, liquid levels, chemical composition, and equipment performance. All of this information is transmitted instantly to central control rooms where engineers supervise the refinery using large digital displays and advanced computer systems. If even a small abnormal condition is detected, alarms immediately notify operators, allowing problems to be corrected before they become serious. Safety is one of the highest priorities because refineries handle extremely flammable materials under very high temperatures and pressures. Fire detection systems, gas sensors, emergency shutdown valves, water deluge systems, foam suppression equipment, explosion-resistant electrical systems, and multiple backup power supplies work together to protect workers and equipment. Emergency response teams regularly conduct drills so they are fully prepared for any unexpected situation. Every section of the refinery follows strict maintenance schedules to ensure that pumps, compressors, heat exchangers, valves, and pipelines continue operating safely year after year. Oil refineries are also becoming more environmentally friendly. Many facilities now recover waste heat, recycle water, reduce greenhouse gas emissions, capture sulfur for industrial use, and improve overall energy efficiency using artificial intelligence and advanced monitoring systems. Some refineries are even being upgraded to process renewable feedstocks alongside traditional crude oil, helping support the global transition toward cleaner energy while continuing to meet growing fuel demand. Once every product has completed processing, it undergoes rigorous laboratory testing to verify its quality. Engineers carefully measure octane ratings, sulfur content, viscosity, flash point, density, and many other characteristics before approving products for distribution. Gasoline, diesel, jet fuel, liquefied petroleum gas, lubricants, petrochemical feedstocks, and asphalt are then stored in enormous tanks before being transported through pipelines, tanker ships, railway tank cars, and road tankers to customers around the world. The scale of a modern refinery is almost impossible to imagine. Many of the world's largest facilities process more than 1 million barrels of crude oil every single day. They contain thousands of kilometers of pipelines, hundreds of storage tanks, dozens of processing units, and tens of thousands of instruments working together as one integrated system. Every minute, enormous quantities of raw crude oil enter one side of the refinery, while valuable fuels and industrial products leave the other, ready to power economies across the globe. Although renewable energy continues to expand, oil refineries remain one of the most important parts of the world's energy infrastructure. They transform a naturally occurring resource into the fuels, chemicals, plastics, lubricants, and materials that support transportation, healthcare, manufacturing, construction, and countless everyday products. Through advanced engineering, precise chemistry, intelligent automation, and continuous innovation, these remarkable industrial complexes make it possible for modern life to function on a global scale. The next time you fill your car with gasoline, board an airplane, or use a plastic product, remember that it all began with crude oil and an extraordinary refinery working around the clock to transform it into something the world can use.